Let's get started. We are glad to have Kei Irie from Kyoto University, who is a recipient of the Frontiers of Science Reward. He will going to give a talk also, and he will going to uh, introduce your closing lemmas for closed geodesics and the minimal hypersurface. Let's welcome.
Okay, so yeah, okay.
Okay.
So
So,
so
so
can you
can,
can you
can you
hear
hear
me?
me?
Okay,
Okay.
so so can I
Can I
start
start
my
my
talk?
talk?
Okay,
Okay.
so
So
first
first
of
of
all,
all,
I
I
thank
thank
the
the
organizers
organizers
for
for
changing the
changing the
schedule
schedule
of
of
my
my
talk
talk
and
and
making
making
it
it
online. And
and so
of course, I feel very honored that our paper has been selected to the Frontiers of Science Award. And that paper is about minimal hypersurfaces. But one of the key ideas in that paper comes from my previous result about closed geodesics. So first I talk about closed geodesics. Um, so okay, so let Mg be a Riemannian manifold, and of course a closed geodesic on M is a map from S1 to M such that the second derivative is constant to zero, and there are at least two viewpoints to study closed geodesics. The first viewpoint is that they are critical points of the energy functional. So we can use the Morse theory to study closed geodesics. And the second viewpoint is that they are periodic orbits of the geodesic flow. So let me recall what are geodesic flows. So for any manifold M, we can there is a canonical one form called Liouville. Sorry, there is a canonical one form called Liouville one form, which we denote by lambda m, which is defined by the following formula. So Q is a point in M, and P is a cotangent vector at Q. So QP is a point in the cotangent bundle, and the B is a tangent vector at that point. And lambda M of V is P times the projection of B. Here, projection is the projection from theta M to M. So this is one form. And then d lambda m is a non-degenerate closed to 2 form. So this is a symplectic form on the cotangent bundle. On the other hand, if we have a Riemannian metric G, we can define a Hamiltonian Hg on the cotangent bundle by this formula. So Hg of Qp is half of the square of the norm of P. And we can define its Hamiltonian vector field xhg by this formula. Here, iota denotes the interior product. And the geodesic flow is the flow generated by this vector field. And it turns out trajectories of the geodesic flow are nothing but lifts of geodesics. So there is one-to-one correspondence between periodic orbits of the geodesic flow and closed geodesics of the underlying Riemannian manifold. So from this point of view, we can use symplectic geometry and theory of dynamical systems to study closed geodesics. So let's recall some important results on the existence of closed geodesics. So on this slide, we only consider simply connected manifolds, and Cg of Mg denotes the set of prime closed geodesics divided by the natural S1 action. Here, a closed geodesic is called prime if it is not a multiple cover of another orbit. So first of all, many years ago, Barkov proved the existence of at least one closed geodesic on the two sphere for any metric using the minimax method. And in 50s, Listernik and Fett proved the existence of infinitely many closed, Listernik and Fett proved the existence of at least one closed geodesic for any simply connected manifold using Morse theory on the free loop space. And in 60s, Gromol and Mayer showed that proved the existence of infinitely many primitive closed geodesics, assuming that the Betti number of the homology of the free loop space is unbounded. And Bigge-Pourier-Sullivan showed that that condition is satisfied if the cohomology ring of M requires at least two generators. For such manifolds, there always exist infinitely many closed geodesics. This is a very strong result, but it cannot cover, for example, the spheres. And for the two spheres, Bangert and Franks proved the infinitely many existence of closed geodesics for any metric G using results from dynamical systems. And for the three spheres, for example, the existence of infinitely many closed geodesics for any metric is still an open problem. However, for generic metrics, so the existence of infinitely many closed geodesics for any manifold with C4 generic metric was established in 80s by combination of results of Klingenberg, Takens, Moser, Hinguston, and Rademacher. So in this last result, this M can be, so this last result holds in any dimension. On the other hand, for two dimensions, we can prove much stronger result that is generic density of closed geodesics. So before stating that result, let's recall what generic means. So for any topological space X, we say that a generic element satisfies a property, say P, if the set of points satisfying that property is residual. Residual means that it contains the intersection of countably many open and dense sets. And if a topological space X is completely metrizable, then any residual set is dense. Now let's state the generic density of closed geodesics, which I proved 9 years ago. So let S be any two-dimensional closed manifold, and G of S denotes the set of smooth Riemannian metrics on S equipped with the C infinity topology on it. This is a completely metrizable space. And then the theorem says that for generic metric, the union of closed geodesics is dense. In particular, there are infinitely many primitive closed geodesics. So this is the generic density theorem for closed geodesics. And the main theorem in the Award paper is an analog of this result for minimal hypersurfaces in high dimensions. So let me first explain the proof of this result, and then I will explain how to extend that argument for minimal hypersurfaces. So my first goal is to explain the proof of this result. And this is actually a corollary of the following even stronger result, which I call strong closing lemma for closed geodesics. So let me state the result. Let SG be any closed two-dimensional Riemannian manifold, and let H be any function S which takes non-negative real values, and that is not constant to zero. Then the theorem says that there exists T in the 0, 1 interval such that the union of closed geodesics of the perturbed metric 1 plus TH times G intersects the support of H. In other words, there is a closed geodesic gamma of this perturbed metric 1 plus THG which intersects the support of H. So this is the strong closing lemma for closed geodesic flows. And on the next slide, I will explain why I call this strong closing lemma. Before that, let me sketch a proof of the generic density of closed geodesics from this closing lemma. So let Ui be a countable basis of open sets, and for each I, consider the set of metrics such that there exists a non-degenerate closed geodesic which intersects Ui. And now I claim this set is open and dense. The openness follows from this non-degeneracy condition, and the denseness follows by taking a small h, which is supported on Ui, and applying the closing lemma for that function h. So we have a countably many open and dense sets, and if G is in the intersection, then the union of closed geodesic is dense. So this is a sketch of the proof of the generic density theorem from the closing lemma. Now let me explain why I call this result strong closing lemma. So closing lemma is an important problem in dynamical systems which can be formulated in the following way. So let X be a manifold, X be a manifold, B be a vector field, and P be a point on X which satisfies a condition called no-wandering, which is always satisfied for geodesic flows. Then in this setting, CR closing lemma says that there exists a vector field B prime, which is CR close to V, and P is on a periodic orbit of V prime. So shortly speaking, CR closing lemma says that we can create a periodic orbit passing through a given point by CR small perturbation of a given flow. So obviously, the statement gets stronger as R gets larger. However, even the C1 closing lemma is very difficult to prove, and it was proven by Pugh for general differentiable dynamics, and by Pugh and Robinson in 80s for Hamiltonian dynamics. And for geodesic flows, which are very special class of Hamiltonian dynamics, so far the best result is the C0 closing lemma proved by Riford, which says that when Mg is any closed Riemannian manifold and P is a point and V is a tangent vector, there exists a metric G prime which is C1 close to G, and such that there is a closed geodesic gamma such that gamma 0 by P and gamma dot 0 by B. So this says that we can create a closed geodesic by a C1 small perturbation of the metric, which corresponds to C0 perturbation of the geodesic flow. So in the proofs of all of these results, one has to choose a perturbation very carefully to get a periodic orbit or closed geodesic. On the other hand, this theorem says that perturbation by any such function h can create a closed geodesic. In that sense, this is very strong closing lemma for closed geodesics. And the proof of this theorem is based on the following fact. So let me first state the fact. So for any two-dimensional closed manifold S, there is a sequence Ck where k is a positive integer from the set of Riemannian metrics to the set of non-negative real numbers such that the following properties hold. The first property is spectrality. That means that for any metric G, Ck of G is an element of the length spectrum, which consists of finite sums of length of closed geodesics. Here, same closed geodesic can appear multiple times. This is the spectrality. And the second condition is continuity. That means that each CK is continuous with respect to the C0 topology on the set of metrics. The third property is while law, which says that for any metric G, Ck of G grows like the square root of K, and by taking the limit, one can recover the volume of the metric G. It in particular implies the local sensitivity. That means that for any metric G, there exists a function h on S taking no negative real values and not constant to zero, such that there exists K such that Ck of 1 plus Hg is larger than Ck of G. This is because the volume of 1 plus Hg is larger than the volume of G. Of course, the local sensitivity is much weaker than the while law, but this is sufficient to prove the closing lemma. And we call we call such sequence of functions spectral invariants. And I will explain how to construct these spectral invariants later. And let me first explain how to use these properties to prove the closing lemma. So let Sg be a closed two-dimensional Riemannian manifold, and H be a function S taking non-negative real values and not constant to zero. And our goal is to show that for any t in the 0, 1 interval, So our goal is to show that there exists t in the 0, 1 interval such that the union of closed geodesics of the perturbed metric 1 plus THG intersects the supportive edge. So suppose that this is not the case. This means that for any t in the 0, 1 interval, the union of closed geodesics of the metric 1 plus th times g does not intersect the supportive edge. Then the set of closed geodesics of the metric 1 plus th times g does not depend on t, because this metric is equal to g on the complement of the support of h, and we assume that no closed geodesic intersects the support of h. So the set of closed geodesic does not change. Then this length spectrum, which consists of finite sums of lengths of closed geodesics, is also independent on t. On the other hand, for any positive integer k, we consider the spectral invariant Ck of 1 plus THG. By spectrality, this is an element of the length spectrum, which is independent on t. And it is not difficult to show that this is measure zero set. This is an easy application of the third theorem. On the other hand, this left-hand side is a continuous function on t by the continuity of the spectral invariant. So this is a continuous function taking values in a measure zero set. So it has to be constant. In particular, Ck of 1 plus Hg is equal to Ck of G for any k, which contradicts the local sensitivity. So this completes the proof of the strong closing lemma, assuming the existence of spectral invariants. And there are two constructions of spectral invariants. And the first construction involves machinery from symplectic geometry called embedded contact homology. Let me explain that theory very briefly. So for any closed three-manifold Y and a contact from lambda, that means that lambda which the lambda is non-zero at every point, one can define a vector space ECHY lambda called embedded contact homology. This ECH is a version of Floer homology, and the definition involves counting embedded pseudo-holomorphic curves in a four-manifold Y times R equipped with a natural symplectic form and a compatible almost complex structure. And for any non-zero homology class sigma, one can define a minimax value, C sigma ECH of lambda, that is a non-negative real number, called ECH spectral invariant. And this vector space ECH1 lambda is infinite dimensional, so it contains infinitely many linearly independent elements. And from the corresponding infinitely many spectral numbers, one can recover the volume of the contact manifold. That is the wide law for ECH spectral invariants. And we can also, and it also satisfies spectrality and continuity, although we omit exact formulation in this talk. So this last bullet is a historical comment. So ECH was introduced by Michael Hutchings in a series of his papers starting from 2002 and has been developed by Hutchings and his collaborators. The Y law was conjectured and proved for special cases by Hutchings and in full generality by Christopher Gardiner, Hutchings, and Ramos. So this is a theory about contact three manifolds. And now, if we have a closed two-dimensional Riemannian manifold SG, we consider its unit cotangent bundle, which is a hypersurface in the cotangent bundle consisting of cotangent vector of unit length. And the Liouville form restricted, so this is a three manifold, and the Liouville form restricted on the unit cotangent bundle is a contact form. So we can consider its ECH. And we take a sequence sigma k of non-zero homology classes of this homology, which satisfies certain conditions. And for each integer k, we define Ck of Sg to be the ECH spectral invariant of sigma k. So this is the first construction of spectral invariants for surfaces. And the second construction uses the volume spectrum, which I will explain later. Okay, which I will explain later. So anyway, so far I have talked about closed geodesics. And there is a very similar story about minimal hypersurfaces. So let Mg be any d plus one dimensional closed Riemannian manifold. And closed minimal hypersurfaces of Mg are critical points of the volume functional defined on the set of closed hypersurfaces in M. When d is equal to 1, they are just the images of embedded closed geodesics. And Lusterneck-Schönrellmann showed that there are at least 3 such geodesics on the two-sphere with any metric. When d is equal to 2, there was a series of important results by Shane Yao, Pete Sachs-Uhlenbeck, and Mick Simon Yao about the existence of minimal surfaces in three manifolds. And based on these results, Yao in 1982 conjectured that for any closed three manifold, there exist infinitely many compact and immersed minimal surfaces. On the other hand, by combination of the results by Almgren, Pitts, and Shane Simon, so these results established the existence of at least one closed minimal hypersurface on any closed Riemannian manifold of dimension between 3 and 7. And behind this result is the following minimax theory. So let M be any d plus one dimensional closed manifold and consider the set Zm of d-dimensional Z2 flat cycles in M, which contains the set of unoriented closed hypersurfaces. So, and this set is equipped with the flat topology, and by the result of Almgren, one can compute the homotopy groups of this space. And it turns out pi1 is Z2, and all higher homotopy groups are 0. So this is weakly homotopic to RP infinity, and So its Z2 cohomology ring is isomorphic to the polynomial ring with the degree 1 generator lambda. On the other hand, for any metric G, one can consider the mass that is the d-dimensional volume functional mg on the set Zm, and one obtains possibly singular minimal hypersurface using minimax theory for this mass functional. For example, minimal hypersurfaces in the previous result by Almgren, Pitschen, Simon are detected by non-trivial element in H1. On the other hand, for any positive integer k, we can consider the minimax value corresponding to lambda to k. So for each k, we consider the set pk, which consists of maps phi from x to zm, where x is a finite dimensional simplex, and the pullback of lambda k is non-zero, and which satisfies a technical condition called non-concentration of mass. And we consider the minimax value of this mass function now over this set of maps pk, and denote the minimax value by omega k of mg. This is called the kth volume spectrum. This definition is due to Marcus and Neves, and essentially the same definition was introduced by Gromov and also studied by Guth. And quite interestingly, this volume spectrum behaves very similarly to ECH spectral invariant. Namely, it satisfies the following three properties. The first property is continuity. That means that for every k, omega k is continuous with respect to the C0 topology on the set of metrics. The second property is spectrality. That means that when d plus 1 is between 3 and 7, for any d plus 1 dimensional closed Riemannian manifold Mg and any positive integer k, omega k of Mg is an element of spec Mg, which consists of finite sums of volumes of minimal hypersurfaces. This was proven by Marcus Neves using a compactness theorem by Ben Sharp. And the Wire law says that for any positive integer d, there exists a positive real number ad such that omega k, so for any d plus 1 dimensional closed Riemannian manifold Mg, omega k of Mg grows like k to the power of 1 over d plus 1, and by taking the limit, one can recover the volume of the metric G up to the dimensional constant ad. This was conjectured by Gromov and proved by Lyukamovich, Marcus, and Neves. The constant A1 was recently determined by Chodosh Mantodis, and as far as I know, AD with the larger one is still unknown. Anyway, given these three properties, it is now straightforward to prove the following analog of the strong closing lemma for minimal hypersurfaces, which now I state. So let Mg be any closed Riemannian manifold with dimension between 3 and 7, and assume that G is bumpy. That means that all minimal hypersurfaces are non-degenerate. Then, for any function h on M taking non-negative real values and not constant to 0, there exists T in the 0,1 interval and a closed minimal hypersurface sigma of the metric 1 plus th times G, which intersects the support of H. We assume that G is bumpy to ensure that spec Mg, which consists of finite sums of volumes of minimal surfaces, is of measure 0. Actually, if G is bumpy, then there are at most countably many minimal hypersurfaces. So this set is countable. So of course, in particular, measure 0. Except for this slight issue, the proof of this result is completely parallel to that of the strong closing lemma for geodesics on surfaces, which I explained. And the bumpiness is a smooth generic condition, so there is no trouble to apply this closing lemma to prove the generic density theorem That means that for any closed manifold with dimension between 3 and 7, and for a smooth generic Riemannian metric, the union of a closed minimal hypersurface is dense. In particular, there are infinitely many such hypersurfaces. So this is the main theorem of the Award paper, which was published 7 years ago. And after that, there has been very rapid progress in the field. And in this talk, I can discuss only 3 of them. I apologize for this extremely biased choice. The first result is due to Mark Snedd's son, who showed that for any closed manifold of dimension between 3 and 7, for a smooth generic Riemannian metric G, there exists a sequence of equidistributed minimal hypersurfaces. The point is to use the full power of the Weyl law, whereas to prove the generic density or closing lemma, we only need the local sensitivity, which is much weaker than the Weyl law. The second result is the second result is due to Son, which says that for any closed manifold with of dimension between 3 and 7, for any Riemannian metric, there are infinitely many closed minimal hypersurfaces. In particular, he proves the Yau's conjecture in full generality. And the third theorem by Chodosy and Bantulidis showed that for any two-dimensional closed Riemannian manifold and for any positive integer k, the volume spectrum omega k of Sg is an element of the length spectrum, which means that this is a finite sum of lengths of closed geodesics. In other words, volume spectrum satisfies the spectrality for closed geodesics. So this gives another proof of the strong closing lemma for closed geodesics on surfaces. Now, given this result, given this result, there are 2 spectral invariants for 2-dimensional closed Riemannian manifolds. One is ECH spectral invariant, and the other is the volume spectrum. Both satisfy C0 continuity, spectrality, and the Weyl law. So I think this is a very natural question to ask if there is any relation between these 2 invariants, namely ECH spectral invariant and the volume spectrum. And if there is any positive answer to this question, it will be a version of the following well-known theorem in symplectic geometry due to Viterbo, Salomon-Weber, and Abondandolo-Schwartz, which says that for any closed Riemannian manifold and any positive number A, the flare homology of the cotangent bundle, truncated by the symplectic action, is isomorphic to the homology of the free loop space, truncated by the length. This is because ECH is a version of flare homology, and the volume spectrum is defined from, in this case, the volume spectrum is defined from the space of 1 cycles, which is not exactly the same, but similar to the free loop space. So if there is any positive answer to this question, it will be a version of this theorem. And I think this is a very interesting direction for future research. And now let me finish my talk with some questions about closed geodesics on manifolds of dimension larger than or equal to 3. So basically nothing is known. Nothing is known about generic density or strong closing lemma for closed geodesics on Riemannian manifolds of dimension larger than or equal to 3. There are minimax invariants defined from contact or symplectic geometry, which satisfy continuity and spectrality. However, I have no idea how to formulate the Weyl law for these invariants. On the other hand, the local sensitivity, which is much weaker than the Weyl law, is sufficient to prove the strong closing lemma. And in this direction, there was a progress in the last year about geodesics of Finsler manifolds. So let M be a closed manifold and F be a Finsler metric on M. We say that F is T periodic, where T is a positive real number, if any non-constant geodesic of this Finster manifold is periodic, and that the period is t divided by a positive integer. And we say that a metric f is near periodic if it can be approximated by a sequence of periodic Finster metrics in this sense. And the basic example of near periodic Finster metric is the Katok's famous Finster metric on the n sphere with only finitely many closed geodesics. And then the theorem by Childs and Tani in the last year showed that strong closing lemma for closed geodesics holds for any near periodic Finster metric. Actually, this result is not exactly written in their paper, but result is a corollary of a theorem by Childs and Tani in a more generalized setting in a symplectic language, and the proof uses pseudo-holomorphic curve techniques and a version of local sensitivity. So I think this is a very nice result. On the other hand, this near periodic condition is very restrictive, and it seems that these metrics are scarce. So this is a very nice closing lemma, but to prove the generic density, I think we need some completely new ideas. So I think I'll stop here. Thank you very much for the listening.
Any question for Kei? So if no questions, then let's thank Kei again.
I think we have stopped in our Zoom meeting.